Hello everyone, this is first video lecture covering section 8.3, chapter 8, section 3 about integral test. So there is a very important connection between infinite series and improper integrals. So first of all, look at this. You think about 1 over n squared. Okay? So this is 1 over 1 squared, 1 over 2 squared, 1 over 3 squared, keep going. Now, by the way, as you can see, you can download my lecture notes from the course webpage. Okay? So you have to print out your lecture note first and put them in on your table, and then look at my lecture videos, all right? Because I'm not going to write everything on here. I'm going to write only the important things here, right? So you might want to put some extra comments on the copy of the lecture notes, all right? So, and we make a connection with this. So this is so 1, 2, 3, say 4. Now, if I draw a top of a rectangle from this point to the left, always to the left, then what happens is, see, because it's y equals 1 over x squared. So 1 over x squared is the mother underlying function of 1 over n squared, right? And then this is 2, 1 over 2 squared, 3, 1 over 3 squared, 4, 1 over 4 squared, and so forth. Then this area of this rectangle is, let's say, your width is always 1 here. So width times height is the area. So your area is 1 over 1 times 1 over 1 square. And this area is 1 times 1 over 2 square. This is 1 over 3 square. And this one, 1 over 4 square, and so forth. So, we know that the sum of the areas of rectangles are 1 over 1 square, 1 over 2 square, 1 over 3 square, and so forth. Now here, for the second term and on, think about this. This time. Those ones, not the first one, only the second and on. Some of those areas of the second rectangles, third rectangles and on is smaller than the area of this region under the graph of y equals 1 over x squared, x equals 1, and x-axis, right? That is less than, I just copy this, the area of the region y equals 1 over x squared, x equals 1, and the y equals 0. Region bounded by this. Okay? So this one. The whole thing. So, that is precisely 1 to infinity, 1 over x squared dx. Right? Improper integral of this function. Alright? Now, as you can see in the lecture note, which I'm not going to write over here, you can go through the lecture note and calculate. This is actually 1. 1 plus 1. 2. So, what does it say? We already calculated this one in section 5.10. If you want, you can go back. And also you can look at the lecture note. I actually calculated. So this is 1 plus 1, less than 2, right? The sum of these all rectangles are, some of the areas of all rectangles are smaller than actually 2, right? This is a positive series. Some of the infinite series is just limit of the partial sum sequence, running toward, right? Keep rising because you keep adding more and more positive terms. Yet there is an upper bound, 2. So you can keep going up, yet there is an upper bound. Bounded above monotonic sequence is conversion, right? Monotonic sequence theorem. So this is convergence series. The reason is the corresponding improper integral was convergent. All right? Here, the important property here is that you can make always under the graph by going this way because your function is decreasing. Continuous, positive, and decreasing. Those 3 key conditions for f is satisfied. Now, for other stuff, for other cases, on the other hand, if you think about this one, 1 over square root of 1, 1 over square root of 2, now, for this, we're gonna make a connection with improper integral of 1 over square root of x. So, if you have a 1 over square root of x, go very slowly. 1, 2, 3, 5. This time, we're going to make a rectangle to the right. Okay? And this point is 1 over square root of 2. This is 2, 1 over square root of 2. This point is 3, 1 over square root of 3. So, the area of the first rectangle is, again, width is 1, height is this y coordinate value of this point, right? Width times height. So it is 1 over square root of 1. This area, width is 1, height is this. So height itself, 1 times height is just height. The area is just same as height. So these areas are exactly these terms, right? So in this case, the sum of the areas of rectangles are exactly the series we are considering, right? But because your graph is decreasing, positive and decreasing, and we draw the top of the rectangle always to the right, so it stays above this graph all the time. So some of the areas of the rectangles will be greater than the area of this region between the graph and the x-axis, right? The area of the region bounded by, BDD means bounded by, so I have to say BDD, bounded by y equals 1 over square root of x, y equals 0, and x equals 1. This region, right? That is precisely 1 1 over square root of x dx. And we know that, so and then if you look at the lecture notes, I calculated that this is actually going to infinity. Alright? So our sum of the rectangles is greater than, should be greater than equal to this area of the region, which is itself infinity. Therefore, this series must be going to infinity. Okay? Again, we made a connection with this series, with this improper integral, right? Mother function corresponding to this series. Here, the key point is this. If you draw your top of the rectangle to the right from an integer point, it'll stay below the graph because it is decreasing and positive. But if you draw to the right, it stays above. So that we can bound given series greater than something, this integral, or smaller than this integral, right? So in the end, we can do the same thing for any function, continuous and decreasing, continuous decreasing. Then, if you draw this stuff to the left, always below. So if this improper integral is small convergent, then from the second term and on, this one will be also convergent. However, if this one is integral, is divergent, like this, then we can do it this way. Okay? Drawing to the right, so, now this rectangular area is greater than this region, and the region is already has infinite, area, then this sum of these area of the rectangles also infinity. And those values will be a1, a2, a3. That's the idea of the integral test, which I'm going to write it here. So, theorem, integral test. So I'm going to cut, the important thing. F is, let's say, continuous, positive, and decreasing. Here I say ultimately. 1 to infinity. And our an is derived from function f, as usual. Then convergence of this and convergence of this integral is equivalent. So that means if it is convergent, then this is convergent. If it is convergent, this is convergent. If it is divergent, then must be divergent. Okay? So counter positive of this biconditional statement will give you divergent means divergent, this divergent means this divergent. So they have the same fate. Okay? And then, and below this integral test, if you see the lecture, I describe, or actually define what it means by ultimately. This means your function at first may be increasing a little bit for a while, but it's after that going down. And still you can use this theorem because this is corresponding to the first few integer terms. As long as it's positive continuous decreasing from 3 and on, we can still use this theorem, right? So when certain property holds after some number and on, right? Not necessarily from the very beginning, but at least after some number and on. If that property holds, then we call it, that property holds ultimately, or sometimes eventually. Okay? All right, so that's what I meant in the middle part of the note, page 3. Okay, so let's do example 1. So show that the harmonic series diverges. By the way, this is the first time doing this recording. Actually, second time. The first time was some of the file was just broken. Something wrong happened. So I decided to check my recording is being done well. I have to check, maybe every 10 minutes. So excuse me. All right. Now, so example 1. Let's show that this is divergent. We already showed this one in previous section, 8.2, using some very elementary approach. Now we want to do that confirm it using integral test. So, solution, your underlying function, mother function is 1 over x. Obviously this is continuous, right? These 3 conditions, positive and decreasing on the whole interval, right? So 3 conditions are satisfied, okay? And then we know that this is divergent, right? Well, we learned at 5.10. What did we learn? Oh, well, anyway, I'm going to just go over this one more time. And actually, in the note, I gave you the actual calculus one more time, right? This is ln of x from 1 to a, and limit a going to infinity, and ln of a going to infinity, so this is going to infinity. It's divergent. But anyway, according to the integral test, if this is divergent, this is also divergent. So, by integral test, this corresponding series also divergent. All right. Now, in 5.10, you learn very important things. That is, this 1 over x to the p power. So in this case, p equals 1. In the previous case, this p equals 1/2 in this case, is convergent if p is greater than 1. Divergent if p is less than or equal to 1. Okay? So using this is recall. Now when p is at least positive case, this is decreasing, right? So we can show that using integral test. So this is page 4, it's theorem 2. Theorem 2. So because of that, and converges if p is greater than 1, diverges if p is less than or equal to 1. Now, I didn't show the proof, but I have to be a little bit careful. If p is greater than or equal to 0 case, p equals, let's say, greater than 0. If p is greater than 0, this is decreasing, right? Then f of x equals 1 over x to the p is continuous, positive, and decreasing on this. So the conclusion is just use integral test, that's all, and combine with this one. However, if p is less than or equal to 0, p equals 0 means constant function, right? then the series is just constant series, obviously divergent, right? Third, if P is positive, no, not positive, negative, sorry. Then 1 over n to the negative power means that this one, think about 1 over n to the negative 2, which is n to the positive power, right? The n to the negative p, and this one is positive. It's going to infinity. Your sequence itself going to infinity, then there is no way your series is convergent, right? So these two cases, divergence is from what we already know. The limit of your term does not go into 0. You remember? If series converges, then the term sequence going to 0. Therefore, contrapositive statement says that if limit of an is not 0, anything other than 0, then your series is divergent. We are using that. The first case, greater than 0, less than equal to 1, and greater than 1 case from integral test, and this one combined. Okay? Anyway, so the conclusion is exactly the same form, right? At the time we call it, this is p-test. Okay? We call it, this one is p-series. P-series test. This is the name for this. Okay? Now, example 2, another application of integral test. Example 2, another. So show that divergence. By the way, I didn't fix this one before, but when I say log of x, in my note that is ln of x. Log of whatever. Okay? Log of whatever. In advanced mathematics, usually log means natural logarithm. We don't use common logarithm. But up to calculus, we have to use, the text we use ln. So just bear in mind that whenever you see log, that means natural log, unless I write it. So for common logarithm, I will write it that way. But anyway, I'm going to write it just ln here. Same thing. We're going to use integral test using ln of x over s. This one is obviously continuous and positive on this interval from 1 to infinity. Usually positive is non-negative. Okay? Non-negative. But what about decreasing? Right? ln of x is increasing, getting larger and larger, but x is also getting larger and larger. So the ratio of this one, are they going to decrease or keep increasing? It's hard to know. So for that kind of case, very often we use derivative. So if you can show that the derivative f prime of x is negative after some values, that means slope of the tangent line is negative, means keep decreasing from some value and on, right? So that's why we took the derivative. So quotient rule, this is f over g, then f prime g minus fg prime over g squared. F prime, 1 over x, times g x minus f g prime, 1, and g squared. So you have a 1. Now we want to know when your derivative is negative, so that decreasing. And because it is positive, the whole thing is negative means that your numerator has to be negative, right? Because then negative over positive, so the whole thing is negative, which means that ln of x must be greater than 1, right? And then x must be greater than 1, which means x must be greater than e. Okay? So, at least e and on, it is decreasing. So we can say that ultimately decreasing. So even though not from the very beginning to the infinity, at least ultimately. So we satisfy all three conditions. Okay? So then the fate of convergence or divergence of this theory is same as fate of this improper integral of this. So if you calculate that, in the notes, calculate ln of x over x dx, definition of improper integral. So I'm going to write it from 1 to t going to infinity, right? And ln of x times 1 over x dx. If you use ln of x, we know that this is du equals 1 over x dx. U du means 1/2 of u squared. That's why you have a 1/2 of u, ln of x squared, from 1 to t. So 1/2 of ln of t squared minus ln of 0 equals 0. Now t going to infinity, ln of t going to infinity. So divergence. So by integral test, divergence. Okay? All right. Now, comparison test. Okay. Let me check the video is recording properly or not. Now, the next one is, all right, so consider this. We know that this is geometric series with common ratio 1/2, so it is convergent. We know this one very well. Then what about, question is, what about, let's say, 1 over 2 to the nth plus 1. So be careful. It's not 1 over 2 to the n plus 1. Plus 1 is outside of 2 to the n, right? This is just geometric series. This is not geometric series. So what do you think? Do you think this one will be convergent? Now, the idea here is that these are all positive series. You keep adding positive numbers. Here, each time when you add 1 over 2, this one adding 1 over 3, smaller number. Next one, 1 over 4, 1 over 5, 1 over 8, here 1 over 9. Always this is, you're adding smaller number. Even though when you add larger numbers, still it converges. There's a plateau. It approaches some positive number, right? Slowly increasing, but ever so slowly, so it converges. Then if you add even smaller positive number, don't you think this gotta be convergent too, right? That's the idea of comparison test, right? Since 2 to the nth plus 1 is always less than 2 to the nth, and the larger series convergent, therefore, smaller series definitely should be convergent, right? Without using integral test. If you try to use integral test over here, that would be hard. Right? We have to do something like this. We don't know how to, well, it is hard to integrate. And we don't need to integrate. if you use this comparison. So this is what we call comparison test. Okay? So I'm gonna write it down here. So, theorem 3, the comparison test. So consider, I'm not going to write every single word here. We're considering these two series. And your AN and BN both are positive ultimately. Again, it doesn't have to be positive from the very first term and on. Just after some finite number of terms, and eventually, ultimately, everything positive after certain terms, we call it ultimately positive. Now, first, if Bn is greater than or equal to An is less than or equal to Bn, ultimately, and the larger series converges, then smaller one definitely converges. Okay? I'm going to do it this way. Alright? Likewise, if this time A is greater than Bn, ultimately, and smaller series already going to infinity, divergent. Alright? So, the positive series can be divergent only by going to infinity. So this is same as going to infinity or divergent, same thing. Then, don't you think the bigger series will be even bigger? So, going to infinity even faster. Also divergent. Okay? So, this comparison test is basically the idea behind this. Now here, what you have to be careful about is that, let's say you have this. Then, if this is the case, ultimately, then convergence of the smaller series, does it mean that convergence of Bn, larger one? Think of this way. Let's say we know that 1 over n squared series is convergent. Does it mean that 1 over n series convergent? No. This is too large. Smaller series can be convergent, yet your larger one still be divergent, right? Or it could be still convergent if you have a 3 over 2. So you never know. So convergence of the smaller series has nothing to do with convergence or divergence of the larger ones, because we don't know how larger this one is, right? So you cannot say this. Likewise, divergence of the larger one does not necessarily mean divergence of the smaller one. You can't say that. Again, if you have a 1 over n squared, this is 1 over n, larger one diverges, yet your smaller one still could be convergent. So you have to use comparison test carefully. When you can compare these two series, one is larger than the other, the way you can use comparison test is by showing larger one is convergent, the smaller one definitely convergent. Or smaller one is going to infinity, therefore larger series definitely going to infinity. Only these two cases, not these two. Okay? Alright. Now, example 3 is determine if sine square of n over n squared converges or not. Now, if you try to use integral test, then you have to have a mother function. That should be this one. And you have to check that this is continuous. Check. Yeah, continuous over continuous, check. Positive, yes. On this one to infinity. What about decreasing this? Unfortunately, sine squared of x is not decreasing. It is up and down, right? Up and down, between 0 and 1 and 0 and 1. So it is not easy to show that this is actually decreasing. Yeah, your denominator is going up, possibly. But then sometimes it becomes 0 and then sometimes positive. So it's not going to be decreasing actually. Every once in a while, sine squared of x is 0. Like sine of pi, sine of 2 pi, sine of 3 pi squared. So it will be 0, 0. In the middle, you have a positive. So up and down, 0 and positive and 0. So it's not decreasing. So you cannot use integral test. But even if you're allowed to use integral test, you don't know how to integrate this one. We don't have any formula for this. We don't know how to integrate this. So in any way, we can't use integral test. Rather, here, we use this. Sine squared of n is, well, sine n is between -1 and 1. But if you square it, it's always between 0 and 1, right? Dividing by n squared, both sides. So what do you get? So this is my bn, this is my an. My an is always smaller than or equal to this one, right? And this one is convergent, right? Convergent by P-series test. Because P equals 2, which is greater than 1, so it is convergent. Larger series convergent, therefore, by comparison test, the smaller series also convergent. Now, the part 1 will be done here. Now, what you're going to see part 2 is not smoothly connecting this. It's going to start in the middle of this. Because initially I tried to make the entire video, big one, and then my phone didn't have enough memory, so it was just deleted, the first part, all right? So I'm recording the first part after the remaining second part, right? So that's why there's just a little bit of difference here. But anyway, the second part will start from somewhere around here. So it'll cover both. First part, second one will cover section 8.3. All right? Okay, thank you.